Well, hello everybody. My name is Andres Fielban from TU Delft, and I'm going to present you a paper in which we optimize the route of a vehicle in a ride-sharing system when users can be requested to walk. So, well, this is the outline of the presentation. First, I'm going to introduce you with some more precision the problem that we are studying, then we're going to formalize it. Then we're going to propose some solutions for these problems. Then we're going to test these solutions with numerical simulations, and with that we can obtain some relevant conclusions and also propose some lines for future research. So, on-demand ride sharing, basically a system that serves the requests as they appear, but in which users can share the vehicle simultaneously, is a promising mobility system. And why is that? Well, because online on-demand systems have become massive and very popular in the last years, mostly because of the app-based systems and the ubiquity of mobile phones. And this massiveness has triggered a lot of scale effects. Basically, it's much easier to match users and drivers, and this enables better quality. However, most of the empirical research so far has shown that when these systems are not shared, which is the most common case, then congestion is worsened. So sharing can be a key tool to fight congestion. So that's why it is relevant to study these kind of systems. However, when we are sharing and when the systems are on demand, meaning that the routes are flexible, they can induce very long and unpredictable detours. So to illustrate what do we mean with this, let me show an example. This is in Santiago, Chile, the city where I come from. So imagine that there is a vehicle that is here, it is carrying some passengers, and it needs to pick up a new passenger over here. So if the service has to be door to door, then the vehicle needs to make all this detour, which requires 3 minutes. This is a real screenshot from Google Maps. Whereas if the user can be requested to walk, then a very short walk will reduce the detour to 0 because the vehicle doesn't need to change the street where it is currently driving. So this is an example that shows that some walking can really be determinant in reducing driving time for the vehicles, but also for those passengers that are over the vehicle right now, or for requests other than this one that are also waiting for the vehicle and want the vehicle to arrive as soon as possible. So what's our approach? Well, we will study the optimal route for a single vehicle in which the sequence of requests is fixed. It was determined by some previous algorithm, and we're now just dealing with how to serve those requests. So our inputs, the inputs of the problem are the following. We have a directed graph with vertices and edges, and we have cost functions, CV and CW, that represent respectively vehicle and walking costs. Please note that they can be evaluated in each pair of nodes. Basically, what we are saying is that, okay, you begin with some edges, but then you pre-compute using the Dijkstra or any other shortest path algorithm, all the shortest distances between each pair of nodes, and that's the input of the problem. When we say costs and not times, it is because maybe if this vehicle is carrying some passengers, then you want to consider that the times are more relevant because it's not only the time for the vehicle, but also for the users that are currently in the vehicle or those kind of things. And we have some requests that need to be served in some order. Each request is assumed to be located over a node in the graph. And we have a route, which is the current position of the vehicle. Actually, this is optional. You could imagine that the vehicle can decide also where to start, for instance. And the same with the last node. So we are showing this example, but it is very easy to convert one problem into the other without changing the algorithm much. So what's the problem we need to solve? Well, we aim to find the stops of the vehicle, x1 to xq. We assume that the vehicle is following shortest paths between these stops. So basically, we are asking for the route of the vehicle, and we want to minimize the following objective function. We want to, which is the total vehicle time that the vehicle needs to tour. So that's the sum of the vehicle time between each pair of consecutive stops, plus the walking time between the stops and the real requests. So this problem can be solved. The first thing that we are going to show is that this problem can be solved in polynomial time. So how do we do that? Well, you can build an extended graph G'. This graph is formed by the root. We also put an artificial sink T, and in between we put Q copies or Q layers of the node set. And the arcs in this extended graph goes from the layer I to the layer I+1, connecting each pair of nodes, but always in that direction, also from the root towards the first layer and from the last layer towards the sink. And what are the costs of the edges? Here we have only one cost, which is if you aim to go from yi to zeta y+1, well, the cost is the vehicle cost of going from y to zeta plus walking cost from this zeta to the real request. So it is really straightforward to see if you look at it with some time, that if we search for the shortest path between the root and the sink, then, and of course that can be solved with the Dijkstra or any other algorithm, then we are solving exactly the same problem. So therefore this problem is polynomial, yeah? Because this is the Dijkstra is a polynomial algorithm, and this extended graph has a size that's larger, of course, than the original graph, but its size is also a polynomial of the original input. However, we also propose other solutions. The first one is a heuristic. Why do we need a heuristic? Because for online applications, the optimal algorithm can be slow. So for the heuristic, we consider two things. One of them is to stop depending on the number of requests. So if I need to serve one request, the only thing we are going to take into account in the heuristic is the current position of the vehicle, the request I need to serve, and the request that comes right after that. So the idea is that the vehicle will find a stop that takes into account how do we leave the vehicle in a good position to serve the subsequent request, but not all the future ones. So we look ahead only at one request into the future. And furthermore, in order to stop depending on the size of the graph, we, instead of performing an exact search for what's the optimal solution for this problem, we execute a local search from the real request. And we are not explaining in detail what does this mean. You can then see it in the paper, but it's basically a discrete version of the gradient method. So this is the heuristic. It's expected to be faster. And we also are going to compare the solutions that we obtain with the no walking solutions, in which the vehicle goes directly to the exact requests. So this algorithm here, of course, is very, very simple, but it's useful to analyze to what extent is relevant to require some users to walk. So now we pass to the simulations. So we first show visually what are the differences between the three methods over a toy network. It's a graph, a grid of 10 times 10. With just 10 requests, we show the routes in two halves. So these are the first 5 requests. This is visiting the exact request, the optimal solution, and the heuristic. Here you can see that the exact request need to make a long detour here. Red arcs are the slowest. These are mid-speed, and these are the fastest ones. So this here, it makes a large detour. The optimal route doesn't make this detour at all, and the heuristic makes a shorter detour. And there's also a detour here that is followed by the heuristic as well, and which is saved by the optimal solution. In the second half of the route, the heuristic and the optimal solution are exactly the same, and two detours are saved, this one over here and this one over here. So you can see that the differences are meaningful, at least from a visual point of view, and that the changes are as one would expect to be. So some detours are saved. And from a numerical point of view, the optimal solution can save up to approximately 20% of the cost of the no walking solution. And the heuristic is about 5% worse than the optimal solution. So it is evident, it is really, really clear that requesting some users to walk is useful because up to 20% of the costs can be saved. Whether to use the heuristics or not is not so clear. For this, we now go to a real life instance in which the differences in computational time can be more relevant. So this is a graph, the real graph from Manhattan with about 4,000 nodes and 9,000 edges. We consider 5 random instances, each of them composed by 4 requests. And here we show the ratios between the costs and the computational time. So you can see that the heuristic can be almost 20% more expensive than the optimal solution. In the worst case, they can be as good in the best case. And in the median and the mean is similar, it's about 5% worse. So this, from the costs point of view, these results are similar from the toy network. Regarding the computational times, you can see that the optimal solution can require up to 14,000 more time than the 14,000 times more time than the heuristic, and in the best case it's 200 times. So in terms of order of magnitude, the optimal solution requires seconds, whereas the heuristic requires milliseconds. So is the heuristic worth using? Well, it depends. So let us synthesize all the conclusions, and in particular, we are going to discuss that. So ride-sharing systems can be greatly improved if some detours are avoided through walking, up to 20%. The optimal solution, as well as the heuristic, can be used for different assignment algorithms that assign vehicles to requests. Yeah, so whatever algorithm you are using, at some point you know the route the vehicle is going, the request and the sequence that the vehicle is going to serve, and in that moment you can apply this algorithm to decide in which order to serve them. And the heuristic might be better for online schemes. So milliseconds is really, really good. If you require seconds as the optimal solution, and you are controlling a fleet of vehicles, then it depends on your computational power and the time window that you have to give the solution. So if this is not online, like you are deciding the route that the vehicle is going to follow, for instance, the following day, then of course you can use the optimal solution and it's better. 5% is not despicable at all. On the other hand, if you need to decide each 30 seconds, each 1 minute, for instance, and you don't have that much computational power, then the heuristic can enable to use this kind of ideas online, and the optimal solution cannot be feasible to solve. So some lines for future research, for instance, including some realistic situations like some passengers can be late or vehicle times can be random due to congestion. How can we combine these ideas with assignment algorithms? What happened with that? In particular, this line of research, we are working on it currently. And pricing. Pricing can be very relevant because we have shown that the overall costs are diminished, but some passengers might be requested to walk long distances and maybe they don't want to do that. So how to distribute the gains in the system to all the passengers through some pricing mechanisms can be crucial in order to convince those passengers to walk. So this is the end. Thank you very much for your attention. If you have any question, I hope to be able to see you at the forum. We can discuss these results. This is a paper that has been submitted, but it is being peer-reviewed right now. So if you also have, we don't have a public version available for now, but we're happy to discuss it if you write me to my email, of course. So thank you very much. See you at the forum. Bye-bye.